Hello all. So in this class we are going to discuss about orthogonal projections. Okay. So let me discuss this with an example. So let us recall these two diagrams. So here W is nothing but here this is for the case of R2 and here this is for the case of R3. Okay. So here W be the subspace which contains the origin O. So let us consider a point P here and we join this OP by a vector U, and the projection of this OP on W is denoted by W1, and similarly the projection of OP on this W2 is denoted by projection of P on W2. Similarly for the case of R3, let P be a point here and let U is equal to P vector, the position vector of the P. Then the projection of this P on this W plane is denoted by W1, and the projection and the perpendicular will be denoted by W2. So what we can tell here is that W1 is will be contained in W. W1 belongs to W, and W2, which is nothing but a perpendicular which is drawn to this W, surely it will belong to W perp. And we have already discussed that W and W perp are orthogonal complements of each other. Okay. So now what you can write is, there comes the concept of projection theorem. See here, W is any finite dimensional subspace of an inner product space V, and U be any vector in V. So then any vector U can be uniquely written in the way of U is equal to W1 plus W2, where W1 belongs to W and W2 belongs to W perp. That is what I have told you with the help of the diagram. So this is what we call as a projection theorem. So any vector U can be written as a combination of two projections. That is, W1 is nothing but projection of orthogonal projection of U on W to W, and denoted by projection of U on W. Okay. Similarly, W2 is the complement of U orthogonal to W, and it will be denoted by projection of U on W perp. W perp is the plane which is perpendicular to W. Okay, that is the orthogonal to W. If so, any vector U can be rewritten in this form, that is, U is equal to projection of U in W plus projection of U in W perp. So if any one is known, that is, if your projection of U in W is known, then we can able to easily calculate the projection of U in W perp. And similarly, if this guy is known, then we can able to calculate the other one. Okay. So here is the formula. They have kept this projection of U in W perp to one side and took this to the other side. So you will be getting projection of U in W perp is equal to U minus projection of U in W. So this 4 can be rewritten. This guy can be rewritten as U is equal to projection of U in W plus U minus projection of U. This will come here. So if one guy is known, we can able to calculate the other one. Okay. So now the following theorem whose proof is an exercise. Okay. So what we come across in the previous topics is any vector U can be written as a linear combination of elements in an orthonormal basis. That is what we have come across in the previous class. So here, if V1, V2, etc. up to Vr is an orthonormal basis, and if U is any vector, then what we can write is the projection of U in W can be written in the same way as we did for the previous case. And also, if you are not having an orthonormal basis, then we can able to normalize it, and then this formula also we come across in the previous class. So instead of U here, we are going to write it as projection of U in W. So nothing will change. Okay. So here calculating projections, you are provided with a vector u and vectors v1 and v2. Okay, so it is easy for us to check that v1 and v2 are orthogonal to each other. That is, the inner product between v1 and v2 is equal to 0. So when you observe 0 into minus 4 by 5 is 0, plus 1 into 0 is 0, plus 3 by 5 into 0 is 0. On the whole, you are getting 0. So what we can tell is v1 and v2 are orthogonal to each other. But when you calculate the norm for these two guys, you will be getting norm of v will be equal to 1, norm of v1, and the norm of v2 is, I think this will also be equal to 1. You will be getting 16 plus 9, 25. 25 by 25 is 1. So you can tell that this v1 and v2 forms an orthonormal basis. So if it forms an orthonormal basis, then we can write the projection of u in w. Okay, so the formula, so in the previous theorem we have a formula, projection of u in w is equal to inner product u comma v1 into v1 plus inner product u comma v2 into v2. So when you take inner product between this v1 and u1, so what you will be getting is 1 into 0 is 0, plus 1 into 1 is 1, plus 1 into 0 into 1 is 0. So on the whole, you will be getting 1 here. And similarly, when you take inner product between u and v2, what you will be getting is minus 4 by 5 plus 3 by 5, which is nothing but minus 1 by 5. That is what written here. So hereafter you will be having the normal multiplication, scalar multiplication and addition of two vectors. So we will be getting the answer like this. Similarly, if one projection is known, that is, if the projection of u under w is known, then we can able to calculate the projection of u under w perp. And what we know is u minus projection of u under w. So simply what we can do is we can subtract these two vectors and write